रब्बि इश्रह ली सदरी वयस्सिर ली अमरी वाहलुल उक़्दतम मिन लिसानी यफ़क़हू क़ौली रब्बि ज़िदनी इल्मा। ऐ मेरे अल्लाह, मेरे इल्म में इजाफ़ा फरमा। Assalamu alaikum dear students. Today is the fifth lecture of chapter number 11, electrostatics. Now we will see the contents of today's lecture. Today we will study about electric potential, potential due to point charge, equipotential surfaces, potential gradient, and electron volt. So our first topic is potential difference. The definition is the amount of work done in moving a unit charge from one point to another, keeping the charge in electrostatic equilibrium inside the field is called potential difference. It is represented by delta V and it can be calculated as delta V is equals to W upon Q, where W is the amount of work done in moving a unit charge from one point to the other, and small q is that unit positive charge. In SI system, it can be measured in volts. Explanation. So you don't know anything about potential difference. So first of all, we have to take 3 to 4 points in consideration before moving forward. Okay, so the first point is, and very important, 4 points is to consider that potential difference is between 2 points. Always. Potential difference, it's not just potential, but it is potential difference between 2 points. So we have to take any 2 points anywhere. It may be in any conductor, any material, in free space. We have to take 2 points. Next, one compulsory condition is these 2 points must exist in electric field. What is an electric field? We have discussed it in first lecture. That electric field is an imaginary area in which one charge can experience a force due to another charge. So these 2 points must exist in electric field. So they can't access or exert any force on each other. Last point is, we choose 2 points and there is electric field between them, and then we use a term that there is certain potential difference between them. Okay, when there are 2 points and these 2 points are in the electric field, so there must consider a potential difference between these 2 points. Moving forward, let us consider this figure. This is positive parallel plate of positive charges. This is the parallel plate of negative charges. So the electric lines of forces are showing as positive to negative. This is a smaller positive test charge. And if it is positive test charge, then it must move from positive to negative. Means the movement of this positive test charge is from A to B point. But what we want to do is, we are going to move it from point B to A against its nature. Okay. Now read this point number 1. Let us consider a charge placed in oppositely charged plates. A charge experienced a force in an electric field if an external force is applied. Means if I want to move this charge Q0 from point B to A, then I have to apply an external force on charge against the field and move it from B to A. Then force must be equal to F is equals to Q naught E. We have studied this formula previously in electric intensity, where E is the electric intensity, Q naught is the charge, this test charge, and F is the electric force. Let WBA be a work done by the force. WBA means work done from moving the charge from point B to point A. Okay, now if I am moving this test charge against the nature, it is covering some displacement. So if I am applying an external force and it is covering from some displacement from point B to point A, then there must be work done on this test charge. Okay, now moving on to another terminology, this is known as potential energy. There must be some relationship between potential difference and potential energy, which we will conclude at the end of this topic. Definition is the change in potential energy delta U. This is a symbol of potential energy, and you can see everything is written, every formula is written with this smaller delta. So delta means smaller changes. Why smaller changes? Because in the previous slide there is one word known as electrostatic equilibrium. We don't want to destroy or disturb the field of charges, so the electrostatic equilibrium must maintain. And how can we maintain this equilibrium? If we move the charges slowly and in smaller intervals. So delta Q of charge Q naught is defined to be equal to work done by the force in carrying the charge from one point to the other against the electric field. Okay, so we all know that work done from moving one point to the other is equal to the energy stored in that charge. So energy and work done are equal to each other. Okay, now showing the formulas in terms of potential energy and work done. So for the first formula, this is delta U. Delta U means change in potential energy from moving a test charge from one point to another. And you know that potential energy is stored in any body when there is a change in position. So delta U is equals to WBA. WBA means work done in moving a test charge or point charge from point B to point A. Now this delta U can be written as UA minus UB, where UA is the potential energy at point A and UB is the potential energy at point B. Okay, now one must say that why this is written as UA minus UB, and why can't we write it like UB minus UA? So there is a difference of potential. We always said that positive charge having higher potential. Always remember this, that positive charges, they are at higher potential, and negative charges, they are at lower potential, because when we draw electric lines of forces, they start from positive charge and they end or terminate at negative charge. So it always written as UA because it has higher potential, minus UB, it has lower potential, is equal to WBA. Now moving to potential difference. What is potential difference? The definition is written on the previous slide. How can we recognize it? That there is a difference of potential between these 2 points. Here I am considering point A and B, and this difference must exist in the same electric field. Okay. Now it further can be written as delta U divided by Q naught. How can we write this thing? Because this potential energy or change in potential energy is because of moving this charge, test charge, from one point to another. So delta U upon Q naught is equal to del WBA upon Q naught. Now we also know this, that delta U is equal to UA minus UB. Okay, so write this thing in front of this equation, and then we can say it where VA and VB are the electric potentials at point PA and B. Okay, now this is the formula which we have studied in the first slide. UA upon Q naught can be written as VA. UB upon Q naught can be written as VB, because work and energy are same thing. So considering work per unit charge is known as potential, work per unit charge is known as potential. So this UA upon Q naught can be written as VA, and UB upon Q naught can be written as VB. Now VA minus VB is equal to delta V, where delta V is the difference in potential, known as potential difference between 2 points. Now further we can write this equation, UA upon Q naught is equal to VA. Then UA can be written as Q naught VA, and QB can be written as Q naught VB, where delta V is potential difference point A and B. Last thing, delta U. What is delta U? This is a change in potential energy is equal to Q naught delta V. This Q naught, which is dividing here, when it goes to this next side of equality, it will going to multiply with this delta V. Now this is Q naught delta V, and this is equal to WBA. Okay. The unit of potential difference is volt, and volt is equal to joules per coulomb. And we know that joule is because of work and coulomb is because of charge, and work is a scalar quantity, as well as coulomb charge is also a scalar quantity. So volt is also a scalar quantity. In just voltage or potential difference, we have to deal with magnitudes. So it is rather easy to deal with scalar quantities. Now another important terminology is known as electric potential. The definition is the amount of work needed to move a unit positive test charge from infinity to specific point inside the field is called electric potential. Now here we are considering this charge Q. It has some specific field, and within that field we are considering this point A. Now far away from this field of charge Q, we are considering a unit positive charge at point B, and this point B is at infinite distance. So what we have to do is we are going to move this smaller positive charge towards this point in the field of this charge Q. Now it is again, we are moving this smaller point charge against its nature. If this is positive charge, if this is positive charge, then it wants to move away from point B. But what we are doing, we are moving this point B towards point A, and we have to move it in smaller intervals, smaller patches, so that its electrostatic equilibrium will not disturb. Now, as this point B is going to be closer with that point A, the potential going to be increases. The potential goes on increasing as this Q naught approaches this charge Q, because now at this point it has zero potential. Why zero potential? Because it is infinite distance away from this charge Q. And when I am moving this charge towards the bigger charge, then they both experiences some force of repulsion on each other, and that is why both having a potential difference between them, and it is now increasing as the distance decreases. Okay, it is represented by V, as we have discussed in the earlier slides, that the symbol of potential is V. Again we are using the same formula, delta V. Delta means smaller. We are just dealing with the smaller distances. So delta V is equals to work done in moving the charge from point B to A divided by Q. Now we know that this is VA minus VB. Delta V is equals to VA minus VB. Now if we are considering this point B at infinity, so if point B is at infinity, then VB is equals to V infinity, and as I have told you earlier that V infinity is at infinite distance, so is equal to 0. Now putting the 0 over here, we have just left with V is equals to W upon Q. This equation can be written as general equation by putting or by removing all the subscripts. So V is equals to W upon Q. It is the same formula that is written in this unit form as well. Now this V has some other name. When one point or point charge is at infinite distance away from the other charge, then this V is known as absolute potential. Absolute potential, or also known as zero potential. Again, remember this V has another name known as absolute potential or zero potential, a point where we don't have to do any work to move a charge. Okay, now the last thing is conclusion. What is the conclusion of this point is the potential difference can be created into absolute potential of a point, but it is equal to potential difference. So means it is again a potential difference between 2 points, but these 2 points are, one is in the specific point area and the other one is at infinite distance away. So potential at a point is equal to potential difference between potential of that point minus potential at infinity. Okay. Again the SI unit is volts. Electric potential at a certain point due to a point charge. Consider an isolated point charge q fixed in space. If a test charge small q is placed at infinity, the force on it due to charge positive q is 0. It is the extended version because we have to calculate the value of that potential now. Now considering a capital charge q, which we have already discussed in previous slide, it has the field represented with these lines of forces, and it is considering as B point. We can name any of these things as A or B, no change at all. Now considering any other point A, and at this point A there is a smaller point charge, small q. Now you are seeing that there are these n number of small portions representing the distance. Delta r means smaller patch of distance between A and B point. Why we are moving this smaller patch? Because we don't want to disturb its equilibrium state. From distance from point 1 to their charge q is represented as r1, and the distance from point A to charge q is representing as RA. Similarly, there can be a distance from point B to Q is represented as RB. Okay. Consider an isolated point charge positive Q. Okay. And this small q. Now what we have to do is, we know that the potential of point B is greater as compared to the potential at point A. Electric field does not remain constant. In order to keep E constant, the test charge is moved through infinitesimally small displacement delta R. I have explained to you this paragraph earlier that we are just moving smaller distances not to disturb the field of this charge, and this charge will be moving from each step one by one. The work done can be calculated as, because it is doing a work against its nature, so this is the work done from moving this charge from point A to point B. Delta W is equals to F delta R, where delta R is the displacement. Now F delta R cos of 180. Now why cos of 180? Okay, so delta R is the displacement from point A to point 1. And what is the direction of electric intensity? The electric lines of forces of this small charge q is away from this field. So delta R is making this way direction and q charge is making towards this. So there is an angle of 180 degree between them. So cos 180 is -1. And we can write it delta W is equals to EQ. EQ is the formula of force, electric force, electric intensity into charge, and this can be written as EQ delta R. This is the equation number 1. By putting the value of E in equation number 1, the value of E is from electric intensity 1 upon 4 pi epsilon naught q upon r square, small q into delta r. Now let the test charge is at large distance RA from charge q. We divide the distance between RA and RB into n number of small equal displacement delta r. The amount of work from point A to 1 can be calculated as, we have to calculate the work done of smaller patches. When the charge is moving from point A to point 1, it can be written as 1 upon 4 pi epsilon naught q small q upon r square into delta r, and delta r is very small. By taking the geometric mean, we can be written as r upon ra is equals to r1r by cross multiplying. We have r square is equals to r1 ra, and we know that delta r is equals to ra minus r1. By putting all the values in equation number 2, we get delta w is equals to 1 upon 4 pi epsilon naught q upon r1 ra. Instead of r square, we can write r1 ra into ra minus r1. Now separating these coefficients on one side and ra minus r1 upon r1 ra. Now separating the denominators, r1 ra and ra are cancelling. Here r1 and r1 are cancelling. So this is your first equation for smaller patch A to 1. Similarly, we can calculate the work done for the other patch from 1 to 2. Similar way, the electric potential energy at distance r from Q is capital Q small q upon 4 pi epsilon naught 1 upon r, and this is the expression to find the electric potential energy. Now for a point charge. V is equals to W upon Q. By putting the equation, we are cancelling this small q from this side and we are left with capital Q upon R. And what this equation is telling us that the electric potential is independent of this point charge because this capital Q is a big charge and it has a stronger field. So whenever there is another test charge or point charge moving in that field, then it has no effect on that bigger charge. So the above equation is used to calculate the electric potential due to point charge. Another topic is equipotential lines. Equi means equal, potential, having same potential difference. So these are the lines or imaginary lines at which electric potential is same at every point are called equipotential lines. How can we draw these equipotentials? Let us consider a smaller charge positive Q. These arrows are showing the direction of electric field and these circular lines or surfaces are known as equipotential surfaces. We can imagine of all the points in an electric field at same potential. If we move a charge anywhere within this surface, potential is same. So if I want to move a smaller positive charge from this point to another, they have same potential, where V1 is known as the potential at point 1 and V2 is known as the potential at point 2, and we know that V1 is closer to positive this charge, so it has at higher potential, and V2 is away from this charge, so it has at lower potential. But because we are saying that it has same potential everywhere, so these two are at the same potential. An equipotential line connects points in space where the potential of an electric field is same. This is the characteristic number 1. Number 2, equipotential lines are always drawn perpendicular to electric fields. Like this, these arrows are the direction of electric field, so these circular shape are the direction of equipotential lines. Another point is, if there are two or more charges, then the potential at any point is sum of the potential due to each charge. What are these? There are many equipotentials. This is because of the negative charge. This equipotential is because of positive charge. You can see the electric field away from this charge, so it is the electric field of positive charge. This is the electric field of negative charge as it is inward towards that negative charge, and there is another equipotential surface between them that is from positive to negative. Such type of surfaces are known as equipotential surfaces. The surface where electric potential is same at every point is called equipotential surface, means this is in 3-dimensional and this is considered as 2-dimensional. Okay, now there comes another point, that what will be the value of work done when I am moving a charge, a smaller charge from point V1 to point V2, from the potential V1 to potential V2. Now if I am saying that these two are at the same potential, then W is equals to QV, small charge into capital V. So if V is same at both points, then W is same. Means there is no work done if we move charge Q, smaller q, in equipotentials. So because energy level is same. So what we conclude that equipotential are those lines where potential is same at every point wherever the charge will move. Now consider the last topic, potential gradient. It's a relationship between electric intensity and electric potential. Another important question. Definition is rate of change of electric potential with respect to displacement is known as potential gradient. Again we are considering two oppositely charged parallel plates. One is positively charged, another is negatively charged. There we consider a charge small q naught which is moving away from its nature, that is from negative to positive. And when we apply an external force, then we have W is equals to F dot delta R, and F delta R, as you can see that they have opposite behavior. Force is from point negative to positive plate from B to A, and displacement is from A to B. So they have cos theta as 1. Here cos 180, that is minus 1. This is minus F delta R. Again applying the value of F is EQ naught. Since electric potential difference between the plates can be calculated as W upon Q naught, by putting the value of W, it's E delta R. And finally we can say that E is equals to minus delta V upon delta R, where delta V is the electric potential, change in electric potential, and delta R is the displacement. And the negative sign indicates because there is difference in direction of force and displacement. So this equation basically is known as potential gradient. It is a relationship between electric potential and electric intensity. And why this equation is repeating in this slide again, because it is an important equation and you have to write this derivation in your questions. Last thing is electron volt. Electron volt is basically the unit of energy, the amount of energy acquired or lost by an electron when it is displaced between 2 points, electron or charge, having potential difference of 1 volt is called electron volt. Means in simple words that electron volt is the unit of energy in atomic physics, as we know that W is equals to QV, and W is kinetic energy in case of movement of charge, so is equals to QV. And we know that Q is the charge number of electron, that is 1.6 exponent minus 19. So this can be written as 1 electron volt is 1.6 exponent minus 19 joules. And this is a smaller unit of energy. If you have any question, kindly ask me on WhatsApp group. I know today's lecture is a lengthy one, but it must have to complete within this day because these all derivations and concepts are interrelated with each other. So kindly see this video twice and ask me any confusion, any question if you have. Thank you. Allah Hafiz.